What's the basic object that we're used to seeing on these kind of lengths and timescales? And that's the proton. It's something which we all know pretty well from just knowing just anything about the hydrogen atom and just all the matter around us. And we've known for a long time various features of the proton, that it has a charge, it's positively charged, it's got a mass, it's got a size and spin. But none of these properties really tell you in any obvious way what's inside of them, what's inside the proton. And even more interestingly, over time, we had more than just the proton itself, which was discovered in the late teens, but over time, especially via cosmic ray physics, through which we discovered even things like antimatter, and especially at the big machines at Berkeley and Brookhaven in the 50s and 60s, with all these new detectors and machines, many new particles were discovered, especially in the 50s and 60s. It was a real sort of just explosion of new particle states that were discovered. But for quite a while, people didn't really know what to make of these. Were all these separate particles? Were there some unifying principles? And the way it turned out that just as in chemistry, I have to make some comment about chemistry, being in the chemistry department, the periodic table is really a testament to understanding you get some information about the composition of the various atomic states without really knowing what's inside. You don't really know that there are protons and neutrons inside an atom, but you can definitely order the states and actually even predict states that were actually never seen before. Similarly, in the early 60s, Murray Gell-Mann and collaborators worked out what was called the Quark Model. They actually postulated that inside all the various particles that were discovered, there are other particles which were called quarks, which have fractional charge, and they could be put in these sets, which essentially were ordered along, say, the number of strange quarks you have versus the down minus up quarks, which in other words is ordering by charge. And they found that there were these sets of particles which also seemed to lead to various spaces that could be filled in. And this was, in some sense, an analog to the periodic table, but for the strongly interacting particles that were discovered in the laboratory. And a nice sort of conclusion to this chapter was in the early 60s, Nick Samios and collaborators in the bubble chamber at Brookhaven actually found the omega particle, which actually completed this set by having 3 strange quarks, and really verified this model. It was a very striking discovery because this state had been predicted on the basis of the Quark model. But at the same time, people started accepting that quarks were actually objects inside these particles. It was a matter of time until people started asking themselves what kind of forces were holding these things together. You could just imagine how strong the forces must be to hold these charges together. And based, for instance, on Yang and Mills's work, which was also done at Brookhaven in the early 50s, one was finally led to the theory of quantum chromodynamics. And this is an interesting interesting connection to Einstein's work, where just as photons are the particles of the electromagnetic field, which is one of the things that Einstein postulated to understand the photoelectric effect. The gluon was postulated as the carrier particle of the color field of quantum chromodynamics, which is the field holding these quarks together. And this subject matter, quantum chromodynamics, is really the core, the intellectual core of what we're really doing at RHIC, and also just of strong interaction physics in general. And it suggests that instead of just being a set of 3 quarks somehow just sitting there in a bag, they're actually exchanging these particles called gluons, and it's this sort of seething sort of mass of particles which would make up this, what we would normally think of as a static proton. But now, say we try to look inside of a proton, try to actually probe its inner structure. Can you actually say, by hitting, say, with an electron, for instance, what they did in the late 60s at SLAC, can you actually see pieces of the proton fly out? So although you can hit it and you can supply momentum to a quark, you can, in principle, you should be able to pull it out and actually see some sort of fragment of the proton fly out. But what happens to this as it gets pulled out farther? Normally, when you pull a particle away from its other particles, the forces between them get weaker, as you would get in gravity or electromagnetism. And so these 2 most important forces in our everyday lives get weaker as the particles get farther away from each other. And so the force drops off as the 1 over r squared, so the energy drops off as 1 over r. And this is basically how most of the forces that we know all around us works. But coming back to the proton itself, these guys found out in the early 70s that QCD predicts that the force between quarks is actually constant with increasing distance. That as you pull it apart, the energy gets stronger and actually increases linearly, just like stretching a rubber band. But eventually, when you stretch a rubber band too much, eventually it's going to break. And eventually, there's too much energy, and another quark and an antiquark can pop out of the vacuum. And this is, in some sense, Einstein's revenge, E equals mc squared, and you actually create particles out of the vacuum. And thus, you end up with 2 particles instead of 1 particle. And so, generically, when people like us talk about particle production, this is really the stretching and breaking of this effective rubber band between the quarks to actually turn a particle into two particles. And so you see now a proton, which is still there, and you also see a pion, which has popped out.